In this video, we are going to talk about split testing, sometimes called A/B test, which is the most common type of testing or experimentation we find in the industry. There are many kinds of experiments depending on what problem you're dealing with. Sometimes you will be dealing with continuous variables, for instance, what price to set for a product. Could be $1, $1.5, $10, and so on and so forth. You might test different ordering or structure, for instance, in what order should the options be shown on a menu or on a result page. Then you have multifactorial cases or multivariate cases, where you have many x's changing at the same time. For instance, you are developing a new drink, you might want to vary the amount of flavor, the carbonation, and the sweetness. There are very fancy methods to test all of these, but we are not going to cover them in this course. In this course, we are going to only discuss one type, and that is split testing. This is when you have only a small number of potential treatments, and so you can test them on an equal number of separate random groups. Usually you will call the groups A, B, C, and so on and so forth. And so this approach is often called A/B testing. The process is simple. You take a sample of people and randomly split them into as many groups as you have treatment options. Then you assign each treatment to a different group, and you compare the outcome for each group. Even if we are doing something that simple, there are many things to consider, and we'll spend the rest of the class discussing them. We won't go into any of the more advanced approaches for this course, but I encourage you to take a specialized course if you want to know more. When you pick a sample from a population and toss a coin or use a random number generator to assign them to various groups, you know that the assignment to a group doesn't depend on a third variable z. So you know that x isn't associated with a confounding variable. In this case, x and z are independent, and that's why sometimes analysts will say that x is an independent variable. Note that when x is not randomized, many analysts still will call them independent variables, which is weird to me because most of the time they are not independent at all. This is why instead I call them explanatory variables. But in the case of a randomized trial, then you can use independent variables. Since x was assigned randomly, without considering potential outcomes y, we also prevent the reverse causality issues. We are not applying the treatment depending on what we expect the outcome to be. Be careful, one issue it doesn't solve is the potential interactions with a confounding variable. This is very important to consider when you interpret the results, and we will see an example on the next slide. So we are facing the question, should we increase or should we reduce the number of events for alumni? What we need to know to answer this first question is, does event attendance increase alumni donation? So we might want to randomly pick which alumni is invited to an event. We have one group A that is invited to the event and a group B that is not invited. Then we run the event and we compare if the invited alumni donated more than the non-invited ones. Potential issues with this approach. It answers a question about the effect of inviting. This is what we randomly split, not the attendance, but the invitation. We couldn't force an alumni who was invited to come. So we didn't answer the question, does event attendance increase alumni donation? We answered the question technically of, does event invitation increase donation? The effect might be different depending on latent factors of the invited person. Maybe if the person is more wealthy, they are more likely to attend and they are more likely to donate. Maybe it depends on the degree obtained, where the person lives, and so on and so forth. So there are still many potential interactions between the invitation and the other factor that might affect the donation outcome. Finally, it might be very costly to run this experiment. Maybe we will fail to invite a big donor and she refuses to donate as a result. So it might actually cost more to run this experiment than to just not run the experiment. One way to go around that is to invite all the big donors and to randomly invite some smaller donors. But then we will know if event invitation increases alumni donation for smaller donors. We won't know the effect for the big donors. So you have to carefully assess the risk for each case and make a decision. One thing to consider when you have your experiment design is the internal validity of your experiment. Internal validity refers to the extent to which we can say that the observed effect in our study was caused by our treatment. There are many potential threats, and here are just a few of them. First, you have selection bias. You are asking, is the exposure to the treatment not completely random? Maybe the people entering the experiment are the ones for whom there is an effect. Maybe the people exposed to a treatment are not drawn from the same population. For example, you want to test a new version of your app and you send an email randomly to people in your current user base. You offer participation in the beta test. The people answering yes might be the early adopters. The other might not enter the beta test. And the early adopters might react differently from the rest of the user base. So in that case, the differences in outcome between the old version of the app and the new version of the app might be due to the fact that they are early adopters and not the common user base. And these effects, these differences, are not due to the new version of the app. A different potential threat is differential attrition. Attrition is when people leave the study, so you can't measure the outcome. People staying in the experiment might be the ones for whom the treatment is effective. For instance, you develop a new gym training program to improve cardio, and you randomly assign people to the new program or the old program. Maybe people for whom the new program is effective will stick to the program, while others will withdraw from the study, so you won't observe the outcome in the end. That will bias the results, and you won't be able to actually say there is a causal effect due to the treatment. It might be just due to the fact that people for whom the treatment was not working withdrew. Then you have time effects. For instance, you start the treatment at different times, and you might have different results because of this. You might run a discount on Friday and no discount on Monday. Is the difference in outcome due to the different days or to the discount? Then you have non-compliance. Maybe one group has a treatment that is difficult to follow, and so they don't apply it correctly, they skip it without you knowing that they skipped it. So you will actually have the effect of being assigned to a treatment instead of the effect of actually applying the treatment, which might be very different. Then you have the threat of diffusion across group, which is often called a spillover effect. For instance, you target an ad campaign to some population on Instagram. This is a treatment group. And you don't show the ad to another group, usually called the control group. The treatment group might talk about the product to the control group, which is a group that wasn't targeted originally. And so the treatment also affects the behavior of the control group. This is a spillover. Another example is that you run a discount program in a store A, but as a result, people living close to store B decide to drive a few extra miles, and they come to store A to get the discount. That artificially lowers the sales in store B compared to if you didn't run a discount program at all. That is also a spillover effect. Then you have the placebo effect, which is very famous. There is research by a friend at INSEAD in France who shows that if you give Sprite in a can of Red Bull Silver, they taste roughly the same, people get better at solving puzzles. But if you give the real Red Bull in a can of Sprite, they don't know they are getting Red Bull, they don't get better at solving puzzle. So the effect is due to believing you got the Red Bull treatment instead of actually getting the Red Bull treatment. This is a placebo effect. People might alter their behavior because they think they are getting a treatment instead of because of receiving the treatment. Then you have demand effects. The tested group might put additional effort to please the experimenter because they think there will be an effect. If you tell the subject you're running an experiment, to increase cardio for instance, they'll push themselves to run more. In that case, the improvement in cardio might not be to the fact that there is a better program, but just because the people want to please the experimenter. And by symmetry, there is an experimenter effect. The experimenter effect is when you have an influence on the result because the experimenter knows there is a treatment. For instance, the experimenter might be more enthusiastic when describing a treatment, encouraging people to perform better as a result. The best way to avoid that effect is not to tell the person in charge of measuring the outcome which treatment was applied. Here are a few strategies you might use to increase internal validity. The first one is not telling subjects which treatment they received. This is called a single blind study. For instance, you might not tell them if they are in the old program or the new program. You might give a fake treatment to the control group, the famous sugar pill. So if you're running a drug trial, you give the real pill to some group and the sugar pill to the other. They don't know if they were given the real treatment or the fake one. You might want to show randomly a version of an ad without letting the group know there is another version. They might not even know that a test is running. This is a very popular strategy in the tech industry. These strategies might reduce the placebo and demand effects, or at least these effects should be roughly the same in both groups. A second strategy is not letting know the person in charge of running the experiment and measuring the outcome which treatment was applied either. If neither the subject nor the experimenter know which treatment was applied, we call it a double-blind study, and this is the gold standard in some fields, especially in pharmaceuticals and medical fields. Then there is external validity. External validity is the extent to which the specific findings of your test can be generalized to other target populations or other similar situations. Some examples that might not generalize well: the experiment was run in a lab, or the experiment was done in a specific age group, or you might have selection bias. For instance, your app was tested by early adopters, so it might not generalize to the rest of the population. Always ask yourself, are the findings going to apply to the population at large? Are they going to apply to different contexts or people or times? This is external validity. To summarize, randomly splitting your sample into groups to run an A/B test should help with confounding and reverse causality. But always ask yourself, how confident are you that the effect is due to the treatment? This is internal validity. And then ask yourself, how confident are you that the effect will be similar in other groups or situations? This is external validity. It's about generalizing the findings.